The purpose of this video is to go through some example problems that illustrate concepts related to nucleophilic substitution reactions, or in other words, that illustrate SN1 and SN2 reactions. This segment assumes that you have mastered the material from the previous segments where we went through the mechanism for SN1 and the mechanism for SN2, and we discussed some general features about those different mechanisms. Now what we're going to do is try to apply that information toward some example problems just to solidify that knowledge. All right, so let's go ahead with that and we'll move on to our first example problem here. Okay, so in this problem, what we are given is an energy curve, or a reaction coordinate, as we've called it previously, as well as some reactants, and we're asked to provide, based on that energy curve and the reactants provided, a reasonable reaction mechanism and to predict the reaction products. So now would be a good chance for you to test yourself by hitting the pause button and working through this problem on your own, and then hitting play to determine whether you got to the right solution or not. We're going to walk through how to arrive at that correct solution now. So we look at the energy curve for this reaction, and as you think back about energy curves, going back to the knowledge that we learned back in chapter 4 about free radical reactions, we talked about energy curves there and said that each transition state, which I'm marking with an X here, denotes one step of the reaction mechanism. So what we're seeing in this energy curve is that this mechanism has to have 3 steps. Step 1, step 2, and step 3. And if we take a look at those 3 steps, we decide which one has the highest activation energy. So the highest energy to go from the beginning of the step up to the transition state here, in green for activation energy for step 1, going from the intermediate energy to the top there for activation energy for step 2, and then going from the intermediate right here up to the top for the activation energy of step 3. We can say with confidence that definitely step 1 is the rate limiting step of the mechanism, the step with the highest energy barrier. That fact that step 1 is the rate determining step is a really excellent clue to us, along with the fact that this has 3 steps in total, that this is our SN1 reaction mechanism that's taking place here. Because if instead it were an SN2 mechanism, we would expect the energy curve to have just 1 peak rather than 3 peaks along that pathway, 3 transition states. So we can definitely say this is an SN1 reaction mechanism occurring here due to the energy curve, and therefore the mechanism that we provide needs to reflect that. So the mechanism for SN1, going through this problem here, the first step of an SN1 reaction mechanism was that the leaving group breaks away, and that's due to the relative weakness of the carbon-bromine bond and the fact that once we break that bromine away, it gives a relatively stable intermediate bromide anion as a result of this step. So we'll go ahead and show the intermediate that results from that, like so. And we'll also go ahead and plug in the bromide anion here, which results from this step as well. And then next step of the mechanism for an SN1 reaction is always going to be either a carbocation rearrangement, and the carbocation rearrangement is a possibility as long as there's not resonance, which there is definitely not resonance here because we're not at the allylic position, and carbocation rearrangement is a possibility if we can do a 1-2 shift to make the carbocation more stable. So we have to ask ourselves, can we do a carbocation rearrangement here? In other words, a 1-2 shift. To look at that, what I'm going to look at is the number 2 position in each direction relative to our carbocation. So we call it a 1-2 shift because we call the carbocation atom number 1. The adjacent carbon atoms are number 2. And it will be any group that's bonded, any methyl group or hydrogen that's bonded at position 2 that can come over in that 1-2 shift to stabilize the molecule. So you have 2 hydrogen atoms here, 2 hydrogen atoms here, and we have to ask ourselves, out of the groups that are bonded here at position 2, is there anything that can come over to position 1, moving over to here to make a more stable carbocation? The answer to this question is no. If we move any of those hydrogen atoms over from position 2 to position 1, or if, say, we even move this methyl group over from position 2 to position 1, the outcome of that would not be stabilization of the molecule. Instead, we would end up going from one secondary carbocation to another secondary carbocation, or even worse, in the case if we move this methyl group over like so, we'd actually end up putting the carbocation at the very end of the molecule then at a primary position. That is a no-go. So here, we've looked for possible ways to stabilize this intermediate. We didn't find any, and so therefore we roll onward with our next step of the mechanism. So no carbocation rearrangement, and thus the next step is going to be that the nucleophile attacks the electrophilic carbon. So our electrophilic carbon, of course, is the carbocation because that's the most electron deficient. Looking for our nucleophile, we have ethanol. Ethanol, our 2-carbon alcohol, recognized as an alcohol because of the OL suffix. So CH3CH2OH can definitely act as our nucleophile, specifically using the electrons from the oxygen. Those lone pair electrons come in. They're very drawn to the positively charged carbocation, so they form a bond to there. And that's going to give us our next intermediate here. So we have our oxygen, covalently bonded to the hydrogen, and covalently bonded to a CH3CH2 ethyl group. That oxygen also still has in its possession one set of lone pair electrons from right here at the bottom. And if we calculate the formal charge on that, we're going to come up with a +1 formal charge for our intermediates here. So then next thing on our roster here is to do something to make our organic molecule have no formal charges to make it a stable final product. So step 3 is that we are going to deprotonate the organic molecule. We're going to remove that proton that's bonded to the oxygen in order to yield the most stable possible product out of this step. So this is going to be our pretty fast acid-base reaction step going on here. So I'm just redrawing what was present there at the earlier step and removing a proton from it. So I'll show that deprotonation taking place explicitly up here. Typically it's going to be the nucleophile that can play double duty, also acting as a base here. So it acts as a base because it's grabbing a proton from our organic molecule, the so-called acid. That forces the oxygen-hydrogen bond to break. And that is going to lead us to our final product, which I should get correct here down at the bottom, that we actually end up with CH3CH2 bonded there to the oxygen, and it's our hydrogen here that has left during the deprotonation step to give us, as our other product, CH3CH2OH2, and we'll have a positive formal charge on the oxygen atom there. So this will take us to our final organic product of this reaction right here. The other piece of the puzzle to ask yourself about is always stereochemistry. So have we created any chiral centers in our product here? The answer to that is yes. Where the bromine group broke away and the alcohol came in and bonded to yield an ether, that is a new chiral center. And since this is an SN1 reaction that involves that carbocation that's planar, we can have that bond showing up as a wedge or as a dash. In other words, we can make either of the two enantiomers. So we'll go ahead and do that. The reaction is not stereoselective because of the fact that we can have the attack of the nucleophile from either the top face or bottom face of the molecule at the trigonal planar carbocation. So we'll go ahead and draw that out. So now let's make sure we've done everything that was asked here of us. Provide a reasonable mechanism. Yes, based on the energy curve below. We did that. The mechanism is reasonable because if our energy curve has 3 steps in total, in other words, 3 transition states, 3 peaks to the mountain, then we should have 3 steps in our mechanism. 1, 2, 3. So we're good to go on that. Our rate limiting step, the step with the highest activation energy, should be step 1. So step 1 is our rate determining step. That's always going to be the case with an SN1 reaction because we're going from something that's relatively stable to start with and creating a carbocation out of that. That's not particularly energetically favorable. There's a high energy barrier to doing that. And then from there we go onward. And we could also say, based on this energy curve, that the reaction we've shown here is an exothermic reaction. The reason we say it's exothermic is because the energy that we're seeing at the beginning of the reaction is greater than the energy at the end of the reaction. So we've gone energetically downhill overall, even though during the reaction we had to gain some energy along the way in order to overcome those activation energies of each step of the mechanism. Okay, on to the next example here, where in this problem we're given a reaction, we're even provided with the product of the reaction, and we're asked, based on this observation of what product we formed, to provide a mechanism that's reasonable for this reaction. So as I always say when we're doing example problems, it would be a good idea to hit the pause button, see if you can do this, and then hit play to make sure that you were on the right track with it. So let's go ahead and get going here with this. So providing a mechanism for this reaction, we're given the reactants and the product. We just need to figure out how we go from reactant to product here. And the observation that we can think about when we're trying to decide upon a mechanism is we can think about the rate of the reaction. In other words, is the rate dependent upon the nucleophile, the electrophile, or both? We don't have that information. We can ask ourselves whether there's a carbocation rearrangement as a possible clue. We see that there's no carbocation rearrangement here, but also we'd predict there's none possible even if there was a carbocation. And we can also look at such things as the stereochemistry and the type of carbon atom that has the leaving group bonded to it. So our type of carbon with the leaving group bonded to it first is a secondary carbon. Our product is a secondary carbon as well. And so in this reaction, since that is secondary carbon, we would say that it could be SN1 or SN2. We have to then go in and think a little bit more about this. What we notice about this reaction, though, is when we come down the list of things to allow us to differentiate SN1 from SN2, is that we have an inversion of stereochemistry going on here. So we have a chlorine that's a wedge becoming a cyano group, CN group, that is a dash. So we've inverted the stereochemistry and going from reactant to product, flipped the chirality, in other words, and that inversion of stereochemistry indicates to us that this has to be an SN2 mechanism because we've inverted the stereochemistry, or we've inverted the chirality there at the chiral center. So therefore, we can say that this is an SN2 mechanism, and we need to write out our mechanism accordingly. So we'll go ahead with this. I'm going to start with my starting material here, our 2-chlorobutane. And the sodium cyanide, NaCN, if we look at the sodium versus the carbon, we're going to see that we would expect the carbon to end up with a negative formal charge, lone pair of electrons on that carbon. And in order to fill the octet for the carbon and take care of all the electrons that would have to be in this structure, we're going to have to put a triple bond in and a lone pair there on the nitrogen to enable us to create the most stable resonance structure of CN using all the electrons that are available for that. So this is sodium cyanide. It's a really common nucleophile, and the trick to getting this right is being able to recognize which atom, nitrogen or carbon, is going to be negatively charged. And here it is going to end up being the carbon that's negatively charged. So we draw the Lewis structure out for CN. It's going to be a carb anion, a negatively charged carbon. Kind of unusual to have a negatively charged carbon, but not impossible. It's going to come in and do that backside attack on the electrophilic carbon that's bonded to our leaving group. Leaving group leaves. And that's going to lead us directly to our product in this one-step reaction mechanism. So our one-step reaction mechanism. Now we need to draw in our nitrile group or cyano group. This CN group has many different names associated with it, like so. And we would also, as a result of this reaction, have chloride anion. And you can write the sodium ion there as well if you want. It is up to you. It's just a spectator ion along for the ride. It's not actually doing anything, so it's not super critical that you show it there, but you can if you want to. So that's going to be our mechanism for this reaction based on the information that we were given about the stereochemistry of this reaction that's observed in the product. All right, so as our next example, we're going to take a look at this problem, where again you're encouraged to hit the pause button and make sure that you are able to do this, where we are asked to predict the product of the following reaction and provide a mechanism for it. And the clue that we're given here is that the product should be a racemic mixture. And you're reminded that when we say the term racemic mixture, a racemic mixture is an equal mixture of two enantiomers. So referring to an equal mix of two enantiomers. And what this is going to suggest to me, since we're seeing a mixture of two enantiomers rather than stereoselectivity, I would expect that this indicates our reaction mechanism is an SN1 mechanism, that mechanism that includes the planar carbocation intermediate that can be attacked from the top face or bottom face of the molecule. So let's go ahead and devise an SN1 reaction mechanism to account for the formation of a racemic mixture from this reaction. All right, so step one, per the usual, we're going to break away the leaving group. So we've got our chlorine bonded to our carbon. That's our weak link in the molecule. And by breaking that carbon-chlorine bond, we're going to yield a carbocation and then a chloride anion intermediate. So we'll go ahead and do that. That, remember, is the slowest step of the mechanism, so I'm just going to label that as RDS to emphasize that fact. So we break the carbon-chlorine bond. The electrons from that bond go onto the chlorine. And then we will go ahead and draw out the intermediate that results from that step. That's going to be a secondary carbocation. So our secondary carbocation landing right there. And we will also have generated, as a result of this step, the chloride anions. I'm going to have Cl, 3 sets of lone pairs it had to start with. It picked up a 4th set by breaking that carbon-chlorine bond. I'm going to show that in blue for emphasis and to illustrate what our electron-pushing arrow was doing there. So that's step one of our reaction mechanism, where the leaving group left. Step two of our reaction mechanisms, we have to ask, is there resonance? The answer is no. Therefore, since there is no resonance, we ask, is there a way we can do a carbocation rearrangement to improve the induction in the molecule? So we're going to look for a carbocation rearrangement here, asking if we can convert the secondary carbocation, that's this guy right here in yellow, into a tertiary carbocation by doing either a 1,2 methyl shift, called a methide shift, or a 1,2 hydrogen shift, called a hydride shift. So in this particular scenario, keep in mind that both of these lines here are leading to methyl groups, CH3s there at the end of the line, and those would be at what we refer to as position 2. So we call the carbocation here position 1, the adjacent carbon atoms are position 2, and it's going to be the groups that are bonded there, the methyl groups or hydrogen specifically, that are fair game to move over in that 1,2 shift. So let's try moving one of those two methyl groups in red over one spot in the 1,2 shift to see if we can create a stabilized carbocation by doing that. So I'm going to take the electrons and the methyl group here, so our CH3 group, the electrons from the bond, all of that over one spot, so a 1,2 shift. And then we're going to draw the intermediate that results from that and see if this intermediate will be more stable than our starting material. So keep in mind here, it's a good idea to be pretty diligent about bookkeeping of where your hydrogens are. So to start with, we had to have a hydrogen right there. So that hydrogen is still here. And now that that methyl group has moved over, and I'll keep that methyl group in green there to keep my color coding going. Methyl group is in green, it's a CH3. So we have that guy right there. We come over to the adjacent carbon, which had that methyl group bonded there. And that carbon has lost a bond, and so therefore it had to become positively charged. So now, comparing the carbocation that we started off with to the one we've ended up with here, we've gone from a secondary carbocation to a tertiary carbocation. Tertiary is more stable than secondary, so this is definitely something that we want to leave in here that we definitely would expect to happen. All right, onward to step 3 of the mechanism. In step 3 of the mechanism, that's where the nucleophile comes in and attacks the electrophilic carbocation, because those are very drawn to each other. So to go back and ask ourselves what can act as the nucleophile from our reaction mixture, it's going to be the alcohol oxygen atom that has those lone pairs of electrons. So we'll go ahead and do that. And I'll actually show that occurring up here in the upper right, and then show the product that we're forming as a result of that down below. I already started drawing in that product, but got a little ahead of myself there. So we have a CH3OH. The lone pair of electrons from that oxygen comes in, forms a bond to the carbon. Make sure you're really specific about where your arrows are going so that I'm confident you know what you're doing and you're confident you know what you're doing. And then we'll go ahead and write in the rest of these parts and pieces. So I'll show that methyl group in green. I'm going to show the other methyl group in red. And then our oxygen and hydrogen and methyl group, I'm going to show all in blue here to just try to color code it the same way that it was as we started into this step. So we've still one set of lone pair electrons on that oxygen. Going to end up with a positive formal charge on the oxygen too while we're at it. All right, so now we're down to the final stage here. And the final stage is going to be that we want for this organic molecule to be as stable as possible. In order for it to be a stable final product, we need to deprotonate it so that it will have no formal charge. So step 4, the last step, deprotonation. And in that deprotonation step, we will show generally our nucleophile coming back in, because in this container there's certainly millions and millions of molecules of the nucleophile, and that nucleophile is playing double duty here because it is able to also, since it has a lone pair of electrons, act as a base to grab that proton from right there, causing the oxygen-hydrogen bond to break. And this is going to be a really favorable step because it's going to yield our stable final organic product out of this reaction. So we'll go ahead and plug in OCH3. So we've made an ether functional group in our final product here, like so. And we also need to show the stereochemistry. It was mentioned up top here that this will be a racemic mix of the two enantiomers. No surprise to us, because at the step over in the upper right-hand corner that I'm highlighting in yellow right here, that's where the nucleophile comes in. That is the oxygen. It attacks the carbocation. It can attack from the top face or bottom face of the molecule, giving rise to the R and S chiral centers at that location. So to get this problem all the way right, spot on, we need to include the stereochemistry here. So I'm going to show that as a wedge, this as a dash, and then I'm also going to show the enantiomer of it. And the way I'll show the enantiomer here is just by changing all the wedges to dashes and dashes to wedges to indicate that we've made the two different stereoisomers at this location that reacted. So here and here we have the R and the S configurations, or in other words, these two molecules, if made in equal quantities, are what we would describe as a racemic mixture of our products. So with that, we conclude our problem-solving session on predicting the products and looking at the mechanisms of some nucleophilic substitution reactions. At this point, you should be comfortable if I give you any combination of an alkyl halide, that is your molecule that has the leaving group bonded to it in the electrophilic carbon, in conjunction with a nucleophile. You should be able to recognize what atom is acting as the nucleophilic atom and use that to replace the leaving group, doing perhaps a carbocation rearrangement along the way as necessary and indicated by the clues that you're given about the reaction.